Thanks for staying on to the last day. Today is my first day. Yeah, so yeah. I'm going to say, in fact, yes, I am one of the organizers who came up only for the last day and just to give his talk over here. So I'm guilty as charged on all 3 counts. To my defense, I was supposed to be here yesterday morning itself, but when I had made my travel plans a little more than a month ago, I did not know my country would do some neighborly incursions, as a result of which our friend in the northwest would close their skies to commercial air traffic, resulting in a huge amount of delays. And I don't think anything I said is incorrect. Anyway, also it's strange that as an organizer I'm giving a talk, but I'm not going to be speaking on my own work. I'll be speaking on the sequence of remarkable result proved by a bunch of 4 papers that happened since 2016 to 2018, the last 3 years, related to the unique games conjecture. So there was some progress. The unique games conjecture, we'll say, as you see, the unique games conjecture is one of the central open problems in the area of probabilistically checkable proofs and trying to understand hardness of approximation problems. And it's been open in a very active area of research since Subhash Kot posed it in 2002. There's been a lot of work going on, both trying to, it's one of these open problems, one of these conjectures which, unlike most other conjectures which most people believe in, the community is sort of equally divided between whether the conjecture is true or false. There is just as many people working to prove the conjecture as many people trying to refute the conjecture. And this one, but one thing that did change a lot of non-believers into believers was the recent 2-to-2 Games Theorem, which was proved last year over the sequence of works. It's actually 4 papers by these authors: Kot, Munzer, Safra, paper 1, Dinur, Kindler, Kot, Munzer, Safra, paper 2, Dinur, Kindler, Kot, Munzer, Safra, paper 3, and finally Kot, Munzer, Safra, paper 4, which was proved in Fox last year, which completed the proof of the 2-to-2 Games Theorem. So what I will do in this talk is I will sort of recall what the unique games conjecture is, why it's an important, this one, talk about how they came to try to prove this unique games conjecture, talk about the 2-to-2 Games Theorem, and the most part of the talk will be related to something what's called the Grassman Graph. This is a graph which is a very interesting graph. It's been studied a lot in combinatorics, but it's not been, the theoretical computer science community has not spent much time working on this problem. This is one of the first applications of the ECS community. So what we'll do is, the first part of the lecture I'll talk about the 2-to-2 Games Theorem, and then we'll go on to the Grassman Graph, why the Grassman Graph will actually lead, trying to understand some properties of the Grassman Graph will lead to understanding, resolving the 2-to-2 Games Theorem, and we'll see how far we can get to the proof. I'll try to give, it's to the extent I understand the proof, we'll see, let's see if we have a 1 or 4. So to begin with, hardness of approximation, we are trying to understand which problems are hard to approximate. There are various problems which you would looking at, say, max cut, max 3 sat, vertex cover. All of these are classic NP-complete problems. We know they are hard to get come up with an algorithm. Unless NP equals P, it's hard to get it's impossible to get an algorithm that solves it solves the exact problem. But these problems, we also know that not only are they hard to compute in their exact version, they are also hard to approximate. And what we are interested in this area is trying to find out how hard, up to what point are they hard to approximate. For example, max 3 sat. Now, what is max 3 sat? Given a 3 sat instance, and you want to find an assignment that satisfies the most number of clauses. Each clause has 3 sat instance, so each clause has only 3 literals in it. I think it's easy to see, it's easy to satisfy 7/8 of the clauses. Trivially, just pick a random assignment. This is going to satisfy on expectation 7/8. This is easy to de-randomize. You can come up with an assignment that satisfies 7/8. Question is, can you do a little better than this? And what we know from the theory of PCPs is, it's unless NP were equal to P, we don't expect to do anything better than this. And how was this theory proved? So just like SAT is the starting point for most hardness reductions, out here, the starting point is what is problem called label cover. So let's actually define what label cover is. So label cover, the instance of this problem comes in several parts. By the way, is it clear what I've written to the backbenches also? Okay. let me know if I had to write bigger. The instance is you're given a bipartite graph, U, V, and some edges across. So the instance has several parts to it, U, V, E. That's a bipartite graph. You're given an alphabet sigma and a set of functions, one for each edge. So that's the instance. Yeah. The instance is this set, and so you're given a bipartite graph with a bunch of edges. There's an underlying alphabet sigma, and for every edge in this graph, phi e, there is a constraint given of this type, sigma to sigma. Every edge has a constraint given to it, and what we want to find, the goal is to find two assignments, one to the right side. So you want to label the right hand side and the left hand side by symbols from this alphabet, such that you maximize a constraint being satisfied. What is a constraint being satisfied? Pick a random edge, UV, and you want phi e of AU equal to B. You want to maximize the probability that this constraint. So I will say this constraint is satisfied. This constraint is satisfied if, say, I color this with alpha and beta, phi of alpha equals beta. We say this constraint is satisfied. So we want to give a coloring to, or coloring or a labeling to the left hand side and the right hand side that maximizes the number of edges being satisfied. This is clearly a much more general abstraction of a standard NP. SAT, 3 SAT can be written in this form, 3 coloring can be written in this form, various of these. So it's clearly this problem to try to find the A and B that maximizes this is a standard NP completeness theory. We'll say that computing, so we'll call this number, well, I'll call this number defined to be this quantity. The value of the instance is a maximum such probability, and computing val of phi is NP hard. This is standard NP completeness theorem. But what this theorem wants to know is what about approximating val phi? And this is where the PCP theorem and PCP theorem plus various several follow-up work together tell you that not only it's actually NP hard to not just compute it, but even to tell apart. I give you an instance and I tell you whether it's perfectly, there's an assignment that satisfies all the edges or an assignment that satisfies at most 0.1% of the edges, and yet we won't be able to tell them apart unless NP equals P. So it's NP hard to distinguish for all delta 0, 1, NP hard to distinguish between instances that are fully satisfiable versus at most delta satisfiable. I'm going to be using this sort of terminology again and again. So let's actually give a name for such problems. So I will call this problem what I'll call gap 1 delta label cover. And I'll put the alphabet to this one. This is a language in which the S instances are those phi such that val phi is, let me write it a little more generally, and let me put C and S for some val phi is greater than or equal to C, and the no instances are those phi instances for which val phi is less than this. And an equal statement of this fact is for all delta, gap 1 delta label cover sigma is NP hard. Because I stated it very, very abstractly at this point. The reason this is a very useful theorem is as a corollary of this, we get the statement that I mentioned. So this is result due to Hastad, that max 3 sat, it's NP hard to get a 7 by 8 plus epsilon approximation. Max 3 sat. And there are several such things. By A, B, it's NP hard to get a n to the 1 minus epsilon approximation for the max clique. For a clique, you can trivially get an n approximation, just output one vertex, that's a n approximation. To do anything better than that is NP hard, and all of these follow from the key ingredient that goes into proving all of this is the starting point is this theorem. Yes. So yeah, so the way I should have stated it, for all delta, to be more precise, I should say there exists a sigma which is poly 1 over delta, such that the corresponding gap problem is satisfied. Yeah. What? No. So right now, the way I have stated it right now, so let me be a little formal given this. This one, the actual theorem will go the following. Right? For all delta, there exists a sigma which is poly 1 over delta, such that gap 1 delta label car sigma is NP hard under n to the log 1 over delta time reductions. So it's NP hard, and the reduction, what does it mean to say it's NP hard? There's a reduction from 3 sat to this, and that reduction takes time n to the log 1 over delta. This is what you get from PCP theorem plus what's called the parallel repetition theorem. Yeah, so for every constant delta, you do get, for every constant delta over here, you do get another constant size alphabet for which this reduction runs in time which is polynomial. Because this doesn't tell you that you can make delta to be subconstant. There are versions of the theorem, I'm going to omit it for now. There are strengthenings of this theorem which will give you also for delta to be subconstant. For now, this will suffice for us. Answer both your questions. Yeah, so this sort of resulted in this understanding this statement of the theorem led to a revolution, and we had a sequence. In fact, there was an industry of results produced from sort of the mid-90s to mid-2000 for several combinatorial optimization problems. We were exactly able to pinpoint the threshold of approximation. We were able to say if you come to this, up to this point, we had algorithms that were able to do this approximation, and anything beyond it was NP hard, and we could start it from this. But what was realized that there were some problems which, despite this good understanding of them, they sort of seemed to defeat this purpose. We did not know how to get the right, the upper bounds and the lower bounds did not match. That is, for example, one such problem is what's the vertex cover problem. Not going to define it. I hope most of you know what the vertex cover is. Again, I want to find a set of vertices so that in a graph of as small a size as possible, so that every edge is incident on this set, the vertex cover, and you want to find, we know this is one of the classic NP-complete problems. We want to find as good an approximation to it. There's an easy 2 approximation algorithm for it, and we want to know if you can do anything better. So what was known in 2000, the work of Dinur and Safra, is that you get a 1.368 approximation to vertex. So this was one of those problems for which the upper and the lower bounds didn't match. The upper bound was 2, that was up to which you could approximate, and the lower bound was from 1.368. A similar problem that was seen is a similar status problem was something called the max cut problem, the max 2 sat problem. We talked about the max 3 sat over here, max 2 sat. Several of these problems had this feature that the upper and lower bounds did not match. So even though we had this good theory and this one, we did not know. And it was at this point, the work of Dinur Safra, followed by Subhash Kot, who realized if we had actually a stronger version of this theorem, then for several of these problems, actually we could come up with the exact approximation. So he conjectured that if the quote, if the label cover problem had more structure, then one could obtain optimal hardness in approximability results. And what was the more structure? So what we'll do is next 5-10 minutes we'll spend on what is the more structure, and that's where both the unique games and the 2-to-2 games are going to come in. Any questions so far? So what's the structure? So let's go back to this sort of thing here. This constraint, already these constraints have a very special feature. They are what are called projection constraints over here. I should have mentioned it, this one. It's the projection constraint has a feature here that once I give a color here, there is a unique color on this side that's going to satisfy the constraint. Because given it at these constraints as functions. If I'd given them as relations, that's not the case. It might be that for every color here, there are multiple colors here that could satisfy. But I already specified the constraint as projections, as functions. For every color here, there was a unique color here such that this was satisfied. This is not necessarily true the other way around. So these were called projection constraints, and the PCP theorem in fact guaranteed that label cover even with projection constraints is NP hard. Actually, it's not a hard exercise to show that if label cover is hard under regular constraints, then it's hard under projection constraints also. It's easy to go from regular constraint to projection constraints. What Court observed, the court noticed that if we had more structure, what is the more structure? Suppose it was unique the other direction also. That is, given the color beta here, if there is a unique alpha here such that this is satisfied. So all the constraints, so what we'll call these unique constraints. The phi e's are bijections. The word unique comes from that. If you had this extra structure on them, if you knew that, then one could possibly do. Another version of it is possibly they are not unique, but they're what are called D2-1 constraints. That is, each of the phi e, for all phi e, the phi e inverse of any beta was of size at most d. For all beta and all e. D to D constraints. So the unique Games conjecture is the unique Games conjecture of R. It's the following, that is, for all epsilon, there exists a sigma such that gap 1 minus epsilon unique Games label cover is NP hard. Right now this is a conjecture. So he assumed that suppose instead of such a theorem, you had a stronger version of this theorem in which it's not fully strong, it's incomparable the way I have stated it, because it's a loss of perfect completeness. Note this is a unique games conjecture, so it's easy to check if it is perfectly satisfiable or not, because you can, if it's once these constraints are unique, you can give one color alpha, that will immediately tell you what's the color beta here, and you can propagate the color. So if it's perfectly satisfiable, you can, just by going over all the possible colors for a particular vertex, you can find out if it's perfectly satisfiable or not. So checking for a unique games instance whether it's perfectly satisfiable is easy. That's why we'll drop the perfect completeness. We will make it 1 minus epsilon over here. And this is what is one version, and the other version is sort of the D to 1. Let's make it the 2 to 1 games conjecture. Both of these were posed in the original paper of proved that for all epsilon there exists a sigma, such that gap 1 epsilon 2 to 1 label cover sigma is NP hard. So if you could make this once, then could sort of observe that if you could strengthen, if one could strengthen this theorem to either of these theorems over here, then one could actually get more. For instance, following a sequence of results due to several authors, what was shown is vertex cover. That is the consequences of such this would be vertex cover is it's hard to approximate vertex cover beyond a factor 2. 2 minus epsilon approximate vertex cover. For max cut, hard to beat the Gomans-Williamson approximation. Max cut for a whole variety of problems. Once you made this extra leap of faith, if you assume the stronger version of the PCP theorem or this label cover hardness, then several of the problems whose hardness we did not know how to match, we were able to match these two. And in fact, there's a long list of problems. Out here, we'll not go into these. We're shown that if you make the stronger assumption, then you can do this. And since actually, even at that point when Subhash conjectured it, he said that if you had this, then you could prove it. I don't think he believed in the fact that this is true conjecture or not. It's unclear why such a statement should be true, and there was a lot of effort that went into also trying to refute this conjecture. In fact, there were work from the algorithmic community primarily due to using sum of squares. One who showed that there is to the epsilon time algorithm to solve gap 1 minus epsilon UG label cover. So you could solve it in exponential time. It's slightly different from typical NP-complete problems, because typical NP-complete problems, one expects them to take purely exponential time, not 2 to the n to the poly 1 over epsilon. And these sort of tell you that it was slightly easier possibly than NP-complete problems. So possibly the unique game conjecture was false. These were kind of giving you reasons to believe in unique games conjecture was possibly false. So this n to the poly 1 over epsilon, sorry, it's n to the poly epsilon. It becomes the polynomial, as epsilon goes closer to 0, this becomes a considerably sub-exponential quantity. So there were both of these sort of to go. And by the way, these sort of algorithms also were able to refute. We had similar algorithms for the 2 to 1 games also. The same sort of algorithmic techniques that came about in the sum of squares approaches these is work. Arora, Barak, Steurer, Barak, Raghavendra, Steurer, sequence of work showed this, that you could have both of this. And yeah. Yeah, that's why I didn't write NP hard over here. So whatever hardness you can prove for this, you basically you can give a reduction from this to this problem. This is what these results show. That is, you can give a reduction from this other problem. So certain basically, if you can get a 2 minus epsilon approximation for vertex cover, then you can break this. Yeah. Alphabet, for this problem to be interesting at all, it has to be, the alphabet has to be at least 1 over delta in size, because if it's not, if the alphabet is of size smaller than it, you can always get such an approximation. A random thing will already get you. So for it to have this gap, the alphabet has to be large enough, and they begin working around that setting. Yeah, so this was sort of the state of affairs till about 4 years ago. Yes. Yes, these are polytime reductions. Once again, like these problems, will be n to the sum, the exponent, it will be n to the sum poly in 1 over epsilon. The reductions will run in those time, but they will think of epsilon as a small but constant always. It's like 0.001 or something, so they will all be polynomial time reductions. So each of these statements are basically, there is a reduction from this problem to vertex, to gap to vertex cover. This problem to gap alpha Goman. Yeah. Is the one-to-one games. Yeah, unique is exactly, it's the one-to-one version of this, in which this is it's a bijection from either end. Okay. So what happened? So, and this was a sort of state of affairs in which there was we had both results. It sort of said, and there were other consequences of the study of UG actually led to other ones which I will not go into. So on one hand, we knew that if you assume UG and these stronger things, you get a plethora of problems whose hardness we could not prove otherwise. But on the other hand, the unique games problem was not as hard as a typical NP complete problem. A typical NP problems, typically you expect to take 2 to the order n, omega n time. This was taking slightly smaller than that. And this was a state of affairs till about 4 years ago, when the work related to the 2-to-day games conjecture. So people asked started off with the work due to Koht, Munzer and Safra, asked, okay, we do not know how to prove the unique games. Can we try to at least attack possibly the 2-to-1 games conjecture? And what this, the first of these papers suggested that if one studies the Grassman graph, which I will define right now, if the Grassman graph had certain specific properties, then some version of the 2-to-1 games conjecture is going to be true. So this is what their initial work led. So let me first tell you what the Grassman graph is, and then state that what, if the Grassman graph had certain properties, then what version of the 2-to-1 games conjecture would be true. So they were looking at, what's the Grassman graph? I'll define the Grassman graph now, but we'll see why it will very naturally arise when we try to attack the 2-to-1 games. So the Grassman graph is the following graph. So there is an ambient space you're working over some k-dimensional vector space over GF2. All of this could have been done over any field, but we'll work over GF2. The 2 here, it's because of GF2, this is going to be 2-to-1. If you had worked with some other field, SQ to the k, this will be a Q to 1. Whatever I say, you'll see it shortly. This one. So the ambient space is this one. We're going to define the Grassman graph. What is the Grassman graph? The vertices of this graph are going to be all L-dimensional subspaces of F2k. It's a set of all L contained F2k. So the dimension of L is L. And the edges will connect two L-dimensional spaces, L and L prime, if their intersection is an L minus 1 dimensional subspace. So its edges are exactly L prime such that dimension of L intersection L prime is equal to L minus 1. So it's this graph in which, so L is 0 is less than or equal to L. Okay, that's, now you're looking at L, the vertices of the graph are L dimensional subspaces, and two subspaces are connected if they intersect on a N. They have a maximal intersection. They are not the same, but they have maximal intersection. And what they showed is if this graph had certain, they had conjectured that if this graph had certain properties, which we'll come to shortly, then the sequence of these theorems proved the following. From the 2 to 2 or 2 to 1 Games theorem, for all delta, there exists an epsilon, there exists a sigma such that 1 minus delta gap 2 to 1. So that's the main theorem that was proved using some properties of this graph. This was the main theorem that was proven, which is almost the conjecture which I have said there, except with a loss in perfect. So this is almost the 2 to 2 Games conjecture of this. This had perfect completeness, and this has 1 minus delta. So it's almost the original conjecture of Cote, except the 2 to it was not. It's not the unique Games conjecture in the sense it's not a 1-to-1, and 2-to-1 it's almost the 2-to-1 except with a slight loss in perfect completeness. And what they showed is if this Grassman graph had certain properties, then it's conceivable that you can prove this. This was the initial work of the first two papers sort of did this, and the subsequent papers tried to understand what properties of the Grassman graph we wanted to study, and eventually the fourth paper in the list actually proved the required property on Grassman graphs. Yeah. So what kind, so this is what I will say. So what kind of consequences this will have? So this, the consequence of this is the fact that vertex cover is √2 hard to approximate. So it beats, so I mentioned the original result of Dinur and Safra had said vertex cover is 1.368 hard. This gets a slightly better hardness by getting √2 hard to it. And for some other, and by the way, so the consequences of, so the consequences of this theorem, in fact, this was the original, actually, the first paper only stated this as the main result. That is, NP hard to get a √2 minus epsilon approximation for vertex cover. But notice from this, you are now given, suppose you are given a 2-to-1 Games instance. From this to go to a 1-to-1 Games instance, what you could do is take every constraint, just change the constraint so that it randomly for every alpha, just for every beta, there were 2 such constraints that's going to be satisfied, just one of them. Just randomly decide which one you get. So you could produce a unique Games instance from a 2-to-1 Games instance. This is a randomized reduction. But what will be the completeness? The completeness will drop from 1 minus delta to half minus delta. You'll only be able to solve half minus delta. So in particular, you will be able to show the following. That is, under randomized reductions, gap half minus delta unique Games label cover is NP hard. So you're almost halfway there. That is, if you didn't want completeness 1 minus delta, but half minus delta, then we do get whatever we wanted from unique Games. And for the inapproximate results which I had mentioned, like the things which I had said, like for max cut, max sat, vertex cover for this one, you need it to be 1, not half. But on the other hand, all the current algorithmic techniques, whatever they work, they didn't really care whether this was half, 1, or 3/4, or 1/10. So this was so the current algorithmic techniques, they were indifferent to what was the completeness. They would have worked just as well for completeness 1 or completeness half or completeness 1/10 as long as it was bounded well away from 0. And this sort of said that given this result, those algorithmic techniques are bound to fail. So it was this consequence of the 2-to-1 Games theorem which basically converted a whole bunch of non-believers in the unique games conjecture to believers in the unique games conjecture, because currently we have no algorithmic techniques. All the algorithmic techniques that were expected to solve UG would have also solved this instance of UG, but now we know this version of UG is hard. Yeah. So there was, after this, due to Subhash and Amay, we have this one, but I don't want to go into. So there's been work on this for which, so there are places where the completeness is not an exact number, but some order log n, order log this one. So if you are willing to, if those places, whether it was half or 1 didn't really matter. So for a bunch of such problems, you actually get optimal even from this as a starting point. So there's a follow-up paper due to Cote and Bangale who proved this. Okay. So what we will try to do, remaining part of this lecture and the next lecture, is try to give a sort of a bird's high viewpoint of how can one prove this, and why does the Grassman graph even enter into the proof of such a theorem. Any questions? Yeah. No. So both possibly I changed the epsilons and delta. So the conjectures which I had put up there in this one, the conjecture which I had put up there, the unique games conjecture was exactly of this form. The 2-to-1 conjecture, the only difference was it was 1. Other than that, it was exactly the same thing as this. Neither implies. This is a weakening of both of them. It's a weakening of both of. It's not either of the conjectures that you want. So in the case of unique games, one can't expect perfect completeness. In the case of 2-to-1, one could potentially expect perfect completeness, but this proof falls short of achieving perfect completeness. And we won't have time to see why it falls short, but yeah, it falls short of achieving perfect completeness. It will be interesting to get even fix this. If I have time at the end of the talk, I'll talk about what can be done we need some algebraic, some other graph structures for which we can try to get rid of this and get a perfect 2-to-1 Games theorem with perfect completeness. That's open. Yeah, I'll come in a minute. So I'll call the 2-to-2 or the 2-to-1 is going to, I'll come to it in a second. So we'll. So how does one go about proving these sort of theorems? So I want to prove the label cover is, given that the label cover is NP, my starting point will be, okay, I erased that. So our starting point will be the previous version of label cover hardness, which we already knew. And from that, we'll try to come to this 2-to-1 Games theorem. So I have a label cover in which I'm not guaranteed of any 2-to-1 or this one. All I know is a projection constraint. And from that, I want to come to a slightly more refined version of label cover in which each constraint is just 2-to-1. So for this, it will be, instead of viewing these as a label cover problem, it will be easier to view it as sort of 2-prover or k-prover games. So I'll first say how the label cover problem, right now I talked about it as a graph problem, a coloring problem, a labeling problem on graphs, but we'll instead just give an equivalent sort of 2-prover version of it in which there's a verifier, there are 2 provers, P1 and P2. What I do? picks a random edge from the graph, sends the left endpoint to the first prover, the right endpoint to the second prover. Each of them returns with a color, and the verifier accepts if CE of alpha equals beta. And any such game, given any such label cover game, I can come up with a two-prover game this way, and what I want to come is a strategy for the provers that maximizes the verifier's probability. This is exactly, I've changed nothing in this formulation of it, and it's also clear that if this game, if the verifier had tossed, in the whole process tossed only log n amount of randomness, then for each of the randomness you could come up with a graph here, and this graph will be at most polynomial sized. You just go cycle over this one. So these two are equivalent formulations of the same problem. It will be helpful for us to view it in the two-prover game structure. And the fact it's two provers comes because every constraint here involves two things over here. If the constraint here involved three vertices, it will be a three-prover game. Sometimes if it involves k, if these were instead of an edge, it was a hyper edge of arity k, this would be a k-prover game. You just have k different provers, the k different vertices, and get the corresponding labels back and accept if the label satisfies some constraint. So the two-prover version of it. So typically, how does one, even before we try to attack the 2-to-1 Games theorem, how does, starting from this, how did one sort of try to prove sort of max 3 sat or max 3 lin 2 is NP hard? So one way of doing it is right now, so this what is it, why is this problem not solving max 3 lin? It's this predicate over here, this predicate. If this predicate, or this test over here, had it been of the form some x plus y plus z equals b, had it been of this form, then this would have exactly solved the max 3 lin 2 problem. Rather, for instance, if you had got three answers, say alpha, beta, and suppose gamma, and these were bits, and it was just checking alpha plus beta plus gamma is equal to b, then if you unravel this, you will get exactly the max 3 lin 2. I'm not sure I'm making sense if people have questions on this. So if this predicate here, right now it's a complicated predicate based on what the label cover problem is. If that predicate was a simple predicate of this form, then we would have got max 3 lin 2. All I want to say. Let's take this on faith now. Question is, if it's not of this form, so what we instead do is, what is this prover is further broken down into smaller provers, say P1, P12, P2 is say broken down to just P21, and we ask this prover not to give us this alpha x, but these all of them hold, so we give them u, and we say don't give me, so you give it u, and you say give me the ith bit. So what they hold is not, they want to return alpha to you, but they don't want alpha symbol from a large alphabet. What you want to return is only bit. So instead of saying, you think of some encoding of alpha, and then I say I don't want alpha, but I want the ith bit in the encoding of alpha. And other prover you ask, I want the jth bit in the encoding of alpha. Similarly here you ask this prover, I want say the kth bit in the encoding of beta, and they say return some answers. They return say what answers, say what should I call them, A, B, and C, and you accept if A plus B plus C sat is 0 or something. So what you do is, instead of expecting the prover to return one particular long answer, you're breaking up this prover into several parts and asking them to return not the entire alpha, but some bits of the encoding of alpha. You can conceivably do this. So you can sort of, this is how max 3 lin 2 is sort of done. So in particular, it follows from, so max 3 lin 2, this is the exact strategy. This is the strategy for max 3 lin. Basically, it was it is exactly the strategy that is used. That is, you take this large alpha, do what is called, this code that is used was, that was used by Harstad was what's called the long code. But here, and they managed to do this. You break this two-prover game, you further refine it by making it a slightly larger prover game, and in which the provers now don't return the original alpha, but some bits in the encoding of alphas and betas, and then you check some constraint. Yeah. Okay, I will. It's linear, it's exactly like max3 sat, but each constraint is 3 bits, and you're checking if the parity of the 3 bits is some other pair. It's constraints of this form, x1 plus x plus y plus z equals b. And these are the constraints. I'll take an extra 5 minutes and stop this one, because I'll introduce where the Grassman comes and we'll stop. So what we want right now is sort of want a test. So the verifier wants to ask two provers, P1 and P2, a test. So he wants to ask them some questions, get back answers, but the answers should have the feature that given the answer to the first prover, there are only 2 possible answers to the second prover, or 1 possible answer to the second prover, and given the answer to the second prover, there's only 2 possible answers to the first prover. It's a 2-to-1 game. So we want to design a test, we want to design a 2-prover game such that the acceptance predicate has a 2-to-1 structure. And furthermore, it has a nice coding feature. You can encode this. But this is our basic problem. We want to design a 2-prover game such that the acceptance predicate here has a 2-to-1 structure to it. And what are examples of such games? That's where the Grassman graph will naturally come to it. Actually, let's break now. I'll come to what the Grassman graph is, because it will be easier to give an example of actually the Johnson test, which will fail for our purposes, which will be a which has the structure but will fail, and then that will lead us to what's the Grassman graph. So I'll do this in the next. So 2-to-1 structure is, what is this? It's exactly, I have just restated the problem here. I want this predicate, it's going to ask some questions to the 2 provers. They're going to return answers. But the answers should have the feature that whatever answer this prover returns, they must be exactly 1. So it must have the 2-to-1 feature. If you given an answer to this, there must be exactly 1 answer to this that satisfies it. Given an answer to this, there must be exactly 2 answers to this that satisfy it. It's 2-to-1. So 2-to-1 is asymmetric. The let me just say what is 2-to-2. So 2-to-2 will be just, you sort of repeat, it's better if you look at it in this version. This is a 2-to-1 game. So this, for an alpha, there are 2 betas. But if instead of this, if I ask instead 2 vertices, u1 and u2, both of which are this one, so I ask the 2 provers not u and v as the questions, but u1 and u2 as the 2 questions. Then notice that, and the check is checked that the broach project to the same value here. This will be a 2-to-2 game rather than a 1-to-1, 2-to-1 game. So that's the only reason why sometimes, for symmetry reasons, we will call this a 2-to-2 game theorem. Everything that will be proved will be actually a 2-to-1, this one. So in fact, over here also from now onwards, I will move on to 2-to-2 structure for the rest of the talk. It's just, the 2-to-2 structure is just a 2-step walk in this label cover problem. So this edge had a 2-to-1 structure, but if this is the edge, this has a 2-to-2 structure. Yeah, so that will be interesting to know if this one right now, So in some sense, these are all NP hard problems. They are all, we are making them in the same, this one. Right now, still vertex cover hardness is a harder problem, seems to be harder. UG hardness could in principle be a harder problem to solve than vertex cover. It might be easier to solve, vertex cover is too hard, but no, and vertex cover might be too hard to approximate within a factor of 2, and yet UG might be easy. We can't rule that out yet.